Okay, let us start Module 2 on operating system. The first section will be on Linux architecture. Before we get into Linux architecture, the first question you should ask yourself is, why do you even need an operating system? Maybe not in every case. If you have a single program that uses a simple instruction set, and you can put that program on the board where the processor is running, you don't need anything else. Microcontroller-based devices that are using sensor controllers are simplistic, and they can actually serve the purpose of running one such program. If you have played around with an Arduino board, it has IOs. The memory is with the processor, and you can put sensors on these IOs. You can run a program. That program will read from sensors, and based on the information it gets, that program will do, and it can send signals out to other devices. So it is a simple loop program. Now, then effectively you do not need an operating system to complicate things. It's much cheaper to just run a simple single loop program putting data output through the ports like this. And no abstraction from processor architecture is needed. You in fact are hard bounded to that architecture now. There is no privilege separation needed because you happen to be the only program, and you can trust yourself to be running right in those cases where it is simple enough. But we just went through our computer systems on the server side. The use cases are not that simple. We have processor systems that are large, and these processor systems have a lot of memory that you put in there. They do a lot of networking, file I/O, talk to other systems, and all of that means there is more complexity involved. They also allow multiple programs to run, not a single program. So in these processor architectures, you need something that can operate at a higher privilege level more than any single program, that can manage that all these programs don't kill each other. They obey some rules, they obey some laws, and something also that makes it actually easy to use the computer system, make calls outside through Ethernet interfaces, use the PCI bus effectively. You may have a SSD driver, link to it, move data fast through that, have great fast memory access, get memory when you need it, let it go when you do not need it as a program. The Linux kernel within the Linux operating system does exactly this job. Linux architecture is fundamentally divided into two pieces: the user space and the kernel. The user space is where your programs will go and run. The kernel is where the operating system will actually manage your user space programs such that they go by the rules, and it'll give them the facilities to do all these functions easily. File system, network management, scheduling, IPC, inter-process communication, signaling, security modules, handling interrupt requests at the processor level, managing memory. The applications that are now running on the user space will still need to access the operating system. And the way applications access the operating system is through a system call interface. Linux has about 380, maybe a little more, system calls that it allows user programs to talk to it. If it is going to do something for a program, it needs the program to talk to it. And for that purpose, the system call interface exists. So you can call the kernel with what you need. Applications can call that system call interface directly, but more commonly there is a standard C library available with several function calls that make calling the system call interface easier. And if the system call interface is simple enough, then that library just makes it easy how to pass the arguments down to the system call interface from user space. So applications will generally call the standard C library, although they can call the system calls directly as well. And we will try both of these as we go forward in our examples. So Linux has a kernel and it has a user space. Now, Linux is also available as distributions, and you may be using different variations. If you have a commercial license, maybe a Red Hat one, maybe a free distribution, especially if you're using one at home, Ubuntu, CentOS. Distributions are also available for special purposes, like Kali for security penetration. There are over 500 Linux distributions. Now, what does it mean to say there is a Linux distribution in the first place? So the Linux kernel is the kernel, and it is versioned, and regular releases of the kernel happen. But then as an operating system, and you use Windows as an example, an operating system as a whole has many more capabilities that make the user experience easier. So a lot of utilities. So the kernel has to be packaged with these set of utilities to make it useful for people to use. So Linux distributions focus on a few things. One, the installation experience. So the distributions will come with an installer that helps you install Linux on the hardware system that you're using. There is a package management system that comes along with it. Now RPM and dpackage are two big ones that are used. And then if you're doing yum commands, you're based on an RPM system. If you're doing apt commands to update your packages, then you're using the dpackage system. But at the end, the package management system is important, because once you get a Linux installation done, you would still want to update packages, you would want to install more packages, and you may want to remove some packages. That's what a package management system does for you then. There is an init process that runs in Linux. It is in the user space. Its job is to manage all user programs for you. Now, that has been standardized more or less on systemd by various distributions, but it is not necessary. So the init system is part of a Linux distribution. And then there is a bunch of distribution-specific software collection. That could go with compiler, C libraries, programming languages, Perl, Python, JDK, different versions, different products, security libraries, OpenSSL, OpenSSH, databases, PostgreSQL, MySQL, web servers like HTTPD, and many more. These go into the thousands. So what Linux distributions do is they get the installer, they get the package management system, they have an init process working, and then they put a bunch of the software that they believe is important for their user of that operating system together. This together constitutes a distribution. Now, what are examples of distributions? There are a few top-level distributions. I mean, you can get the kernel anyways, but then there is a front-level packaging that happens, and Debian, Fedora, OpenSUSE are top-level distributions. And then distributions derive from these distributions, so that once they've done the high-level packaging and collection, then you derive to, okay, now let me get a little bit more specific with what my needs are. So Debian has derivations in Ubuntu, Kali Linux. Fedora is the base for Red Hat Linux, CentOS. And Red Hat is just a commercial Linux distribution for enterprises. You pay money for commercial support. CentOS is the community-supported Linux distribution equivalent of Red Hat. So, and OpenSUSE is used in the derivation of SUSE Linux. Here below is also a table to understand how are these distributions packaging things together. Now, one thing that is important to compare distributions is what kernel version are they using. Now, the latest kernel version that is being developed is in the 5.x series today. That's released 2019. There are still versions running from 2004, 2006.x.y versions that are still there. So when you hear, say, RHEL 6 or CentOS 6, you're really talking about the kernel version that is 2.6 series. And Ubuntu was packaging the 2.6 kernel in their 6, 8, and 10 versions. Now RHEL 7 and CentOS 7 use the 3.x version of the kernel. Similarly, Ubuntu 12 and 14 use the 3.x version. RHEL 8 has gone to the 4.x version. Ubuntu 16.18 have gone with the 4.x version. Ubuntu has a Ubuntu 20 on the 5.x version, and RHEL and CentOS has not released a 5.x version yet, but they will release one soon. It'll probably be called RHEL 9. And over time, new kernel releases happen, and these distributions absorb the new kernel and then keep on patching the new kernel over time, and then put a bunch of their own software to package it into a distribution. So how do you tell which Linux you're running? Well, here is a simple command. You can do uname and space -r. It will tell you the Linux kernel version that you're running. You can also do a cat-on /etc os-release, and that will tell you the actual distribution that you're running from the distribution version. So these are standard commands available to you. Your distribution may have something more specific to help you with what version they're running, but these generally should run on the major distributions. Linux is so vast, but Linux is also open source. How do you learn Linux? And the way I learned Linux a lot, and whenever I need to understand a few things, is just go to the man pages. These are Linux manual pages. Now the man pages would be good to understand from a top level structure on how are they divided. There are 8 sections of the man pages. Section 1 is with the command line interface. User commands. You can go and type these commands on a Linux box and they will do something for you. Now, not all distributions will have all the commands, but these are generally the commands available for you. And there may be more that are not in these man pages, specifically in one website. Section 2 has system calls, and these are the Linux kernel system calls that are available. So when you want to understand the system calls that a kernel has and a specific kernel version has, you go to the section 2 of the man pages. Section 3 has the standard C library that comes on top of the system calls and helps you connect, make the system calls on your behalf, and several other standard library functions that are available for you. Section 4 is a lot about devices from the /dev folder primarily. Section 5 gets into the file system and file specifications. Linux is predominantly file driven. Configurations are in files. Statistics, parameters, how is the kernel running? Linux puts everything into a file. So the concept of files in Linux is very important. And section 5 details out the file system specifications as well as file configurations that are there. Like what is the format of a /etc/hosts file, or within the /proc folder, /proc/some file, what is the spec for that? Or just a file system, XFS file system, what is the spec for that? The other sections, section 7 is about overviews, conventions that are used. And section 8 is about system administration commands that are only used by super user, root users, specifically for administration purposes. That sums it up for Linux architecture at a high level. Within this same module of operating system, we will still be covering the next section on Linux system calls and on Linux processes. All right.